Where we got off yesterday. We didn't get too far, but, you know. All right, so this is basically what we got from yesterday. Ideas. What we might do. Well, first let me set a timer because I get carried away. I want to spend 6 minutes max on this. Yeah, go.
Okay, I had an idea.
All right, give it to me.
So, we know that 12 and 27 are perfectly lined up, so the squares are edge to edge, okay? Now, since that's a straight line, we know that...
Go. It's okay.
Hold on.
What?
We know that this is this part
Yep.
of this. Okay,
Right.
so what we can do is we can find out how much this side is, which is 27 divided by 2, if I remember correct.
I know what you're saying. Yep, okay.
To get the square. Then we're going to do 12 divided by 2, get this, then subtract this from the 12 to get this. Then
Logic is good. So we're doing second
That.
addition postulate. So these numbers represent the area. So we're not going to divide by 2. And we don't know that they're squares necessarily, right? If we did, we'd say that the squares side were root 27 by root 27, right? Because root 27 times root 27 is what gets you 27, right? So we can assume they're squares and try to solve it from there. That's what third hour did a little bit. They messed around with some stuff. But your logic is good. If we knew this side here, and we knew the whole thing here, right? So we knew the sides of these boxes, we could subtract from them and get this edge. And if we knew the sides of this box, then we'd have that, right? And we could use those two to find the hypotenuse. Yep, that's true. And then we'd have a part of this side. Logic is good. So write that down if you want to put it on your thing as a
I did by that,
conjecture.
that's a defect.
So that's the idea. If we only knew those sides, we could do that. The question is, how do we figure out those sides? What else you got for me? Not sure. Go ahead.
Well, first of all, it's not right, so, but I added 12, 47, I got 42.
Right, okay.
And then, like, on the other side, it can be the same. And then, so, like, the 3's lined up to half. So then, like, 42 plus 42 is 84, so I can do it.
So are you saying the box of 3 here, that's the area of that box, not the height,
Yeah.
but the area is lined up here somehow?
Kind of, yeah.
Okay, so we could stack that on both sides. That's true.
It's just like, yeah.
So we've got 40, what do we got here, 42, right? So area of 42, if we were to stack those all together, we should be able to make some kind of other rectangle that has an area of 42. We could situate those over here with the other 12, right, the 3 and the 27. Where they would fit and where they would go, I don't know, since these aren't around to scale. But she's onto something. Take a look at this. And then I would extend this, but it's already extended. If I draw a line here, and I'll draw it, don't I have 2 lines cut by another? So this is a transversal. This is 90, right? Are these corresponding? They are. So by cap converse, these 2 lines must be parallel. And if those lines are parallel, then this is a transversal as well, right? Which means these 2 angles are the same. Same thing for this guy, right? Just same crap, just down lower. So these are all the same. Now what do we know about these 3 triangles?
They're congruent.
Nope.
Similar.
Yep, angles is not enough to prove them congruent, but they are similar, right, by double angle. So all these triangles are similar, which means if we find one, we kind of get them all, right? They're all related by some factor,
I
right?
found the one.
What?
Okay, the one with the 12 and 27. I found out that the hypotenuse is 8.5.
Wait, from here to here?
No, the 12 to the 27.
Okay, from here to here.
12 to the 27. Yeah, that's
How do you know it's
8.5.
8.5?
Well, to find area of a square, you usually multiply 2 sides together. Since it's a square, we know that each side is the same. So if I were to divide the 12 by 2, that
Right, you would get 6, and if it was 6 and 6, what would the area of the square be if I gave you a square that's 6 by 6? 6 times 6 is 36, right? So what you really want is root 12, because root 12 times root 12 gets you 12, right? Now, that would be this side here if this were a square, which we do not know, right? You're assuming that this is a square. It could just be a rectangle. What if it's 3 by 4? Now, could you solve the problem by saying, look, I'm going to assume this is a rectangle, it's 3 by 4, and go from there? You could. I'd give you self-development points for that because it's a similar related problem, but it doesn't solve the problem that we're at right now.
isn't there a 90-degree thing though?
There is. Remember, rectangles also have 90 degrees, but their sides might be different lengths, right? That's the difference between a rectangle and a square. Rectangle can have one side longer than the other, whereas a square has all the sides the same, right? So we can't assume that this is a square. I know it looks like, maybe if you count the squares, that it looks like a square, but it's not drawn to scale. I just use these guys to help me draw straight lines. Yeah.
It looks like the midpoint of the big square is right at the edge of the 27 right there.
Looks like the halfway point between here and here. If it were, right, if we assume that, maybe we could solve some stuff. Yeah. We don't know that for sure. Again, it looks like it, but we don't really know. That's a good point, right? If that were the midpoint, how would that change the problem? Would you be able to solve it from there? Again, don't be afraid to make assumptions and solve a similar problem. Not the same problem, but a similar problem, right? If you want to explore that for self-development, go ahead. Or do it now. Maybe you learn a bit about the problem, and then you're able to come back and solve the more complicated one. That's a good point. If these triangles are similar, right, all these angles should be the same as well. What about this triangle? Will it be similar to the rest? And how do we know? I'll give you one more hint. This is a square, right? They told us it was a square. So all these sides are the same. What's also true about a square?
Each side's the same. I'm sorry,
Each side's the same, and then, yes, and all the angles are the same. And what are all the angles?
90 degrees.
90. So this is 90, right? This is 90. This is 90. This is 90. So what does that tell us about this triangle? Owen, you with me?
Yeah.
How can we figure out about the angles in this triangle? Nellie's right. So, check it out. This right here, all those should add up to 180, right? So we have red plus blue and whatever's left over. Well, over here, don't these all add up to 180? And they're red plus blue plus what's left over. So what should the leftover be here? What color? Green. Now, Nellie, if this is green and that's red, what should this be? It has to be. It's the leftover, right? So that's blue. If I were to make this a right triangle, which I can, right? I can always drop a perpendicular. What color would these angles be? I'll give you a hint. What color would that be? Green. Which means this one would have to be blue. I thought about this the other night. What if I drop a line from here? What do you see? A giant square. And all those triangles will be congruent. Because aren't these sides all the same for the square, right? The square. So that means we have the hypotenuse. And if we only knew that the legs match, we'd be able to prove they're congruent, right? Why do these legs match here and here? Or here and here? Or here and here? How do we know those legs match? We don't. Well, what do we know about the angles of this triangle? Look at this big triangle right here. You guys see it? What do you see? Yep, right angle, a green angle. What should this be then? Right angle and a green angle. What must be left over? Blue. Right angle and a blue angle, what should that be? Green. Which means this is blue. And because that's blue and red, that means this has to be green. And because that's green and red, this has to be blue. And that checks out because now we have green, red, and blue here. So now we have angle, side, angle that are the same problem, right? We've got green angle, the hypotenuse, and the blue angle. Green angle, hypotenuse, we know those are congruent because this is a square, right? All those sides are the same. So that means all these triangles are congruent. Same thing down here. Will that help? Will it not? I don't know. But it might. If we could find the area of the whole square, we could subtract these triangles and get what's left over. But we need to know the dimensions of these triangles. Now, right now, the only triangle that I see that we might be able to figure out is this one. Because it has this in it, and that box touches that. We've got a bunch of triangles here. If we can figure out one of these right triangles, we win. Question, how do we get it? How do we get it? Here's my thought. Right triangle. Right? If I could figure out what this diagonal was, I could figure out how these sides relate. Because, well, actually, no, that's only if it's a square. Darn, I was going to say these two sides would be the same, but we don't know that. Yeah, tough. Extend these sides out. Right? Now they go to the sides. Tough problem. Alright, put it away. Alrighty, period 4, we're here. We learned about a bunch of centers yesterday. We learned about the Bisector or the Centroid. G in this diagram is made by the medians, right? Median is vertex to midpoint. And where they intersect, or where they're concurrent, right? Point G. We call it the Bisector or the Centroid. It's the center of mass, the balance point for the triangle, right? And then we said, well, if it's the balance point of the triangle, if I'm trying to balance something, will I ever try to balance it over here? No, it'll always be somewhere on the object I'm trying to balance. So will the centroid ever be outside the triangle? No, right? It's a balance point. It's going to be on the triangle somewhere. Cool. We also learned that the relationship here, and we kind of did this last week, is 2 to 1, right? This part's always double this part. This part would always be double that part. This part would be always double that part. We can prove that. We'll do that next week. Okay? But you need to know it for now. How do we feel about medians in the centroid, or medicenter, whatever you want to call it? Feeling okay with that? Right? Makes sense why it's always inside. It's the balance point. Right? And again, make sure that you know that it's vertex to midpoint. That's how medians are formed, right? Vertex to midpoint. Cool. We also learned about angle bisectors, lines that cut the angle in half, right? All intersect at the incenter. And it's called the incenter because why? Why is it called the incenter?
It's in the center.
Well, all these are technically centers, but yes. It's inside the triangle, always. Why is it always inside the triangle? How do we know that? I mean, we played around with GeoGebra, but how would you know? Just take a look. The incenter is always the same distance from the sides of the triangle. Always. Now, why are those 90 degrees right here? Because when we measure something, we measure perpendicular to it. Here's what I mean by that. If I were to measure from the top of my head to the ceiling to figure out how much room was in between it, I'd measure like this, right? If I didn't measure like this, which is perpendicular to the ceiling, right? And I measured like that, would I get an accurate reading? Here's how high my head is from the ceiling. Very, very, very far, right? No. Still pretty far, but not quite as far. Again, we measure perpendicular to the object. So like when you're standing back to back with somebody, you measure like this, right? Perpendicular. I'm going this way, this is going that way, it's 90 degrees here. A lot of you guys are like, look, I'm the same height as that person, right? That's not measuring perpendicular. Don't do that. Yeah, exactly. Look, we're the same height. So when we measure from G to the sides of the triangle, we can't just, measure anywhere. We want to measure fairly. So we measure perpendicular to what we're measuring to. Does that make sense? Right? Like I would measure perpendicular to the ceiling to figure out how much room is between me and the ceiling. So the distance between G and the sides will always be the same. Now if I've got a point, and I draw lines that are all the same length from that point, what do I end up getting? What do I create? If they're all the same distance, whoops. I do infinitely many of these. What do I get? They're all the same distance. Circle. Right? They're all radii. Right? They all start at a center point. They all go out the same distance. They're radii. Radiuses. Right? So, a point that's the same distance to all the sides. There must be a circle there somewhere. Here's the circle. Are you ready for it? That's a radius, and that's a radius. So those 3 points must be on my circle, right? Here's the circle. That's it. So if you had a triangular box, and you wanted to see what's the biggest ball I can fit inside this, right? You'd find the in-center and measure the distance from there to the side. And that's the biggest ball you can make. It perfectly fits inside the box. It touches the box at one point on each side. So we call it the in-center because it's the center of a circle inside the triangle. Okay? So the in-center, center of an inscribed circle. Now we call it inscribed. Scribe means to write, right? That's what this is, inscribed. Scribe means to write, in means inside. So it's written inside, right? Drawn inside the circle. Or drawn inside the triangle, I should say, right? An inscribed circle is inside the triangle. So an in-center is the center of the circle that fits inside the triangle, right? Because it's the same distance from all sides. So no wonder the center is always inside the triangle. The circle's inside the triangle. If I've got a circle and it's inside a triangle, will its center ever be outside the triangle? No. Here's my circle. It's inside this triangle. Where's the center? Over here? Over here? No, maybe you're really bad at finding the center of a circle, but you'd never be like, is that the center of the circle? Is that the center? Right? Maybe you'd say this. No. If the circle's always inside, which it is, inscribed, right? Then the dot, the center will always be inside. So all of these are the same distance from their sides. So the angle bisectors all intersect at a point, and it's always inside the triangle because that point is the in-center, and the in-center is the center of an inscribed circle. A circle that's inside the triangle. Now, if we have a circle, we know that we have radii, right? So that point's on the circle, which means if I draw from here to here, that'll be a radii. And this point is on the circle, so I draw from here to here, that's a radii. And this point's on the circle, so I draw from here to here, that's a radii. I could draw a radii here as well, but that's not nearly as interesting because this radii also doesn't just touch the circle, but it touches my triangle, right? Now be careful. Look up here. A lot of people will think that that's a radii. It's not. It's slightly bigger than the radii, right? It goes outside the triangle. This one's really easy to see, or easier, right? See how it goes outside the circle? So the angle bisector doesn't always give you the radius. Now this one right here is pretty close, right? Here's the angle bisector here. It looks like, oh man, it might be the radius, but it's not. It has to be 90, right? So these are the angle bisectors. And notice how they're not always going to give you the radius, right? You got to get pretty lucky for them to actually be the radius. Is everybody cool with that? Right? The radius is from here to where it touches the triangle. Don't think that that's the radius. That's actually a little bit longer. Okay? Cool. All right. So, let's play around with GeoGebra. I did show you GeoGebra yesterday, right? Oh, I remember. I know what we were doing.
Because we had Juan, Jacob, and
Well, I had other classes in here.
Bailey.
That's how you spell Bailey's name, right? Her parents were like, let's name her Bailey, but let's be obnoxious about it. And the doctor's like, wait, you're already naming her Bailey. Isn't that obnoxious enough? And they're like, no. So they named her the most ridiculous way to spell Bailey ever, which I came up with a more ridiculous way.
Bailey.
So, here it is.
Sounds like Michael Jackson. Try to say Bailey.
Yeah, that's right, Bailey. All right, so here we go. I'm going to make the in-center. The in-center, what do I need to make to find the in-center? What lines do I need to create? You can look at your sheet. Nope. The in-center.
Well, I know how to make insecurities.
What lines do I need to make to find the in-center?
Angle bisecting lines.
Yep, I need to bisect my angles, right?
Probably next.
So there we go. There's the angle bisector, right? It cuts that angle in half. It is a coincidence that it looks like it hits in the middle, right? It won't always. We see that. But it always does cut that angle in half, because that's what I created, an angle bisector. I'm going to bisect Jacob in half. Rip. There we go.
Not
and then,
real.
again, two lines intersecting. Two lines intersecting, not rare, right? It happens all the time. It'd be rare if they did, right, the parallel. But three lines intersecting is really freaking rare. And look, they are all concurrent, right? They all intersected at one point. So right there, because it's the intersection of my angle bisectors, that is our in-center. Now the in-center is the center of an inscribed circle, right? So there should be a circle in here that perfectly fits inside the triangle. So here's how I'm going to find it. I'm going to measure perpendicular to the side. So I'm going to choose a side that's not very perpendicular. So I'm going to go from here and measure at 90 degrees to here. Okay, so there's 90. Which tells me that this point must be my radius, right, from here to here. So I'm going to highlight this so you can see it. Let's make these bisectors red. So that's an angle bisector, that bisects this angle, and that bisects this angle. So those are the lines that cut the angles in half, right? Those are my angle bisectors. They intersect at the in-center. That's my perpendicular I used to measure the outside. Okay? So that means if I make a circle, starting here, okay, yes, I will be there. All right, so here's my circle, starting at the in-center. If I stretch out to this point, it should perfectly touch every side of my triangle. You guys see that? So I measured from here to here at 90. So that's my radius. Now if I move my triangle, the circle stays inside. Because it's an inscribed circle, right? It's a circle that fits perfectly inside the triangle. Angle bisector where they intersect is the in-center. And then this length right here is the radius. Same thing from here to here. And from here to, oh, I guess we'll both here to there. Right? Radius about there. Radius here. Radius there. So no matter what I make, the in-center is always inside the triangle. Because the circle is always inside the triangle, right? So the in-center is the center of the angle bisectors. Remember, angle bisectors are those red lines that I deleted? They cut the angle in half, right?
Graph the nerds.
Brace the bus. All right. Come on in, but don't be loud. All right, so terminology. The angle bisectors
Cool kids, right?
are these orange lines, right? They cut these angles in half. This angle gets cut in half. This angle gets cut in half. And this angle gets cut in half. Where they intersect is the incenter. We call it the incenter because it's actually the center of an inscribed circle. Inscribed, in means in, so inside. Scribed means written, so written or drawn inside the triangle. Inscribed. Now, because the circle is always inside the triangle, the point, the incenter, is always inside the triangle, whether it's acute, right, or obtuse. The reason there's a circle that fits inside here is because if you measure from G to the outside of the triangle to the edges, right, it'll always be the same distance. And where we have the same distance, we have radii. So we can draw a circle there. This is one of our most complex ones. For those of you just tuning in, we also know about medians, right? Where they intersect, right, going from vertex to midpoint, will produce the medicenter or centroid, whatever you want to call it. And that's the balance point, center of mass. And of course, the balance point's always inside the triangle, no matter what kind of triangle we're looking at, right? If I have an object, the balance point's never going to be off the object, right? It's always going to be on it somewhere. Make sense? Okay. We also know that this is in a 2-to-1 ratio. Let's talk about another one. Let's talk about orthogonals. Now, orthogonal is another name for perpendicular. So all we know is that these are the heights of the triangle, right? It's just 90 degrees. Do they cut the other side in half? Do they cut the other angle in half? No, we don't know any of that stuff. All we know is that it drops from above to 90. Drops from above to 90. Drops from above to 90. Oops, sorry. Drops from above to 90. Okay? And where they intersect, we call the orthocenter. So perfect timing, braces bust. You just got back from the orthocenter. Now, the orthodontist straightens your teeth, which is why when we think orthocenter, we think about 90-degree angles, right? Yes? Congratulations, slimy teeth. She does, and it's spectacular. All
I
right.
don't need braces.
So, the orthocenter. Now, the orthocenter doesn't have a lot of interesting properties, but since these are all right angles, this is a right angle too, right? Aren't these all right angles? You guys see that? Bare hands. Don't these two angles form an X, so they're vertical? So I've got a right angle here and a green angle there. A right angle here and a green angle there. What do we know about those two triangles? They're similar. Don't we have vertical angles here too? We've got an X, right? You guys see that? So I've got a right angle and an angle, a right angle and an angle. So what do I know about these two triangles? I'll say it again. I've got a right angle and a blue angle, and I've got a right angle and a blue angle. So what do we know about these two triangles? By angle, they're similar, right? So these are similar to themselves, right? The blue ones go together. And then lastly, let's do purple. These angles are vertical too, right? Here and here. So now I've got right angle and purple, These triangles are similar. So it's kind of like DB cuts this triangle in half. We've got a blue, a purple, and a green triangle here. And it kind of sends it through this dot and dilates it out the other side. Remember dilations, right? They shrink or grow from point. So it's almost like that little guy got shot through this dot and expanded. Same thing with the blue, got shot through this dot across here. And the greens got shot as well. So it's like through there, through there. Kind of like a dilation. It's kind of what similar triangles are. Right? They're connected by a scale factor, times 3, half, double, triple. So it turns out all those triangles will be similar, and there's some really cool properties that you can prove with that, but they're kind of too advanced for us. I spent all last night doing it and trying to think of a way I could make it more, like, accessible, right, for the proof, but I think it's too involved for now, which is unfortunate. This is the first time I think we've ever done something where I've been like, you know what, that might be a little too hard for now. All the rest were like, no, let's just do it. And you survived. All right, so that's the orthocenter. It's not very interesting. Let's talk about whether it's an isosceles, or I'm sorry, an acute triangle, a right triangle, or an obtuse triangle.
I'm an obtuse triangle.
So, where will it be? Well, for acute, it looks like it'll be inside, right? Spoilers, all of them are inside for acute, right? But will it always be inside? Now, we know the in-center is always inside because it's the circle's inside, right? If the circle's inside, then the center of the circle will be inside, right? We know this is always inside because it's the balance point, right? You're never going to have a balance point off the object, right? Now, this one, there's no reason it can't not be inside all the time. Let's think about a right triangle. Draw it here for me. So, right triangle. What do I need to draw to find the orthocenter? What lines connect to make my orthocenter? What lines do I draw that shows me the orthocenter will be? What are they called? What lines are those? DB?
Aren't they called vertexes?
Nope.
Oh,
It's from the vertex down to 90.
oh, perpendicular.
Perpendiculars, right? Heights, orthogonals, right? That's what I'm drawing. Perpendicular lines. So I'm supposed to go from a vertex down to the opposite side at 90 degrees. So for instance, on here, here's a vertex. If I go down to the opposite side at 90, there it is, right? Where would the other two perpendiculars be? Because we find at least one more, we'll see where they intersect, right? Where would they intersect in a 90-degree triangle? Where do you think? Start here. Now draw a 90 degree to the opposite side. Where would that line be? Well, if I drew a line like that, would that be 90? No, right? Getting closer to 90. That's 90. Here's the line. Right? It's the other side at 90. If I do anything like this, it'll be too big. And boom, it's right. So that's where it hits. Where's the other one? Here. So where is the orthocenter? Yeah, where's the orthocenter going to be for a 90-degree triangle? On the 90-degree vertex, right? Makes sense. We already have two right-angle lines, right? Where do they intersect? There. Where's the other one going to be? I don't know. Also there. Right. So for 90 degrees, it's there. On 90-degree vertex. So, as we go from acute, and we start widening this angle, it starts heading this way, right? When it's 90, it's exactly on the vertex. So as I stretch this triangle and make that angle wider, it sends this guy that way, and eventually it touches that vertex, right? The 90-degree vertex. If I keep stretching it to make it obtuse, right? I went from here to here, right? If I keep stretching it, where's it going to end up? If I keep stretching that triangle, I stretch it a little bit, it goes from inside to here. I keep stretching, where's it going to end up? Well, it's going to keep moving in that direction, right? Stretching makes it move this way. So if it's on here, if I keep stretching, where's it going to end up?
There.
Outside, right? Somewhere around here. It came out the back end. Let me show you that. So here's our triangle.
Khalil J.
Let's make the orthocenter. I need orthogonals, right? I need 90 degrees. I need height. So what I'm going to do is I'm going to go do a perpendicular line from here to this line. Hits it at 90. Do we see that? This line right here is an orthogonal. It hits the other side at 90. I'm going to do the same thing for all my sides. And where they intersect will be the orthocenter, right? The center of the orthogonals. So from here to 90, oh, I was really bad. There's 90 degrees. There's our orthocenter.
Yeah, I know.
If I draw another perpendicular, right? I've already got this side's perpendicular and this side's perpendicular, so I need this one. Khalil. Where's the Khalil?
Khalil Palm.
Nelly? Khalil? Got it. So there's the orthocenter. As I drag this to make it a 90-degree triangle, look where it heads. It heads towards the 90-degree vertex. So if I keep stretching this angle out, right, it's going to go outside.
Wait a minute.
Right, it's going to keep heading in that direction. Here's acute. Here's right. Obtuse. So the orthocenter ends up outside. Here's why. The height of this triangle is right here. Between here and here. You guys see that? That's the height of the triangle. You ever seen a diagram like that? Let me draw it out for you. If you have an obtuse triangle, here's an obtuse triangle. The height of this triangle is here. Right? Does that make sense? So the orthogonals are the heights. I can keep going, right? The height is only from here to here, but I can keep going. Same thing if I rotate this. Now this is the base. If that's the base, the height's going to be here. Right? 90 degrees. And if I keep going, they're going to intersect outside the triangle. Here the height's really easy. It's there. Remember, these lines extend. So they're going to intersect outside. Height of the triangle is here. Keep going. Height of the triangle, here, keep going. They're going to intersect outside. So, for orthogonals, outside the triangle, when it's obtuse, inside the triangle when it's acute, on the 90-degree vertex when it's right. I think this one makes a lot of sense, right? Because there's two 90s coming together already. Talk about perpendicular bisector and then we're done. So, here's what we call this. We call this the circumcenter. Now, if you go to the orthocenter to get orthodontist stuff done, what do you go to the circumcenter for? For your circumference.
Oh.
Right? And circumference means circle. So, circumference means circle. Where's the circle? It's not inside, no way, right? Turns out G is not the same distance from the sides like the incenter is, right? G is the same distance from the sides. G is the same distance from the vertices. These will all be the same. Does that make sense? G is the same distance from all the vertices. Now, if we have a point, and we have a bunch of lines sticking out in the same distance from it, what do we get? A circle. Now, where's the circle going to be? This is the radius. Where's the circle going to be? On the outside of the triangle. Right? We call this a circumscribed circle because it's on the outside, like circumnavigate, right? Go around the world. To cut around the world, right? So we have a G is the center of a circumscribed circle. Scribe means to write. Circa means to like circumnavigate, go around, right? We'll finish this up tomorrow and then review. This will basically be your quiz.
Damn.
No warm up tomorrow. Almost done. So close. Tomorrow we'll talk about when it's acute, right, and obtuse. Yes, I do. Just when I get all the way.
Time in 6th grade when Mr. Young said that I should quit band now because I'm never going to be anything.
Yeah, Zero hated you.
Oh, Mr. Young hated me, yeah. I was a little bit annoying as a kid, yeah, but still, Jesus, Mr.
Yikes. Sorry. Bye, Nelly.
I remember my old band instructor, Mr. Young, said I should quit band because I'll never be anything.
I heard that. So, shout out to Macy. Here's the deal. You're gonna be okay. We just gotta get these different things down. So, angle bisectors make the in-center. In-center's inside the circle, inside the triangle. So the center will always be inside. Talking to Macy, she's absent. Then the orthogonals always intersect at where the 90s are, right? The orthocenter is what we get. That's inside on acute, on the vertex for a 90, and then outside for an obtuse. That's right. And then perpendicular bisectors, they form this center. It's called the circumcenter because it's the center of a circle that goes on the outside of the triangle. We'll talk about that more tomorrow. And then medians intersect at the center of mass called the centroid or medicenter, and that's always on the inside. Medians are the vertex to the midpoint. Good luck, Macy. See you tomorrow.
I'm gonna run to the bathroom.